Welcome to the second video in which I will discuss some of the critique on magnitude-based inference. It is important to understand the critique on the method so you can make a decision on whether to use the method or not. I won't discuss all critique in detail. For more details, I recommend you to read the papers, which I have referred at the end of the presentation. For now, I will just discuss a few critique points and the responses by Hopkins and Batterham, and occasionally I will also provide my own thoughts on the issue. So, the first critique point. If a well-trained volleyball player improves his jump height by 3 centimeters, would that be a relevant change? And if it is, would we classify it as a large or a small improvement? Or if we have a 10% decrease in the number of injuries due to a 10-week intervention for a whole soccer team, is that a relevant decrease? And if it is it small, large, or very large? In both cases, it is difficult to provide an answer to the question. Therefore, Cohen and later Hopkins provided some guidelines on how to interpret the magnitude of an effect when no other guidelines are available, as you can see in the table on the right. For example, both Cohen and Hopkins suggested that a change or difference of smaller than 0.2 standard deviations would be too small to be relevant, while a change between 1.2 till 2 standard deviations would be classified as large in the Hopkins scale. It should be noted that the guidelines by Cohen are based on social and behavioral sciences. However, in a critique paper, Watson correctly suggests that this classification should be done with care and can only be done when some assumptions are met. One argument that is important to consider is that the same mean effect can have different magnitudes due to the differences in the standard deviation of the samples. For example, consider two interventions. In the left figure, here this one, we have a group of very homogeneous individuals with a small variability and therefore a small standard deviation as indicated by the small error bars on the bar graphs and the really narrow normal distributions. This group trains on strength and improves by a mean of 20 kilos. In the right figure here, we have a heterogeneous group with more variability and therefore a larger standard deviation, again indicated by larger error bars and a more wide normal distribution. They also improve by a mean of 20 kilos, so the mean improvement, as shown by the error bars and the vertical red and blue lines, is the same in both groups. It's really important to keep this in mind. But the standard deviation in the right group is much larger. Therefore, the effect size is also smaller. Indeed, the left group improves 3 standard deviations. You can see from the red line has moved up 1, 2, 3 blue dotted lines, so 3 standard deviations. While the right group, the red vertical line, has moved only just a little bit less than 1 standard deviation. You can see here the effect is less than 1 standard deviation. Here it's 3 standard deviations. So it is indeed important to not blindly trust the effect size and also look at the actual data. But magnitude-based inference also states to take care with standardization, so I don't consider this a particular limitation of magnitude-based inference. Further, it is important to note that it's not necessarily wrong to consider the change in the left group as very large and the change in the right group as as moderate, even though they both have the same mean change. For example, if the left group would be a small group of elite sprinters, they are probably much less variable than a group of recreational athletes. For the elite sprinters, it would indeed be much harder to make them improve by 20 kilo if they already have a lot of training experience, in contrast to the right group of recreational individuals. So an improvement of 20 kilo for the elite sprinters could indeed be considered as very large, and for the left group, but for the right group of recreational individuals, it could indeed be a moderate improvement. And further, in null hypothesis significance testing, some researchers are also increasingly reporting effect sizes, and they are also required for sample size estimation in equivalence testing. So I don't think it's a specific limitation for magnitude-based inference, but it's definitely important to consider the limitations of effect sizes. In the previous video, I briefly explained 3 forms of magnitude-based inference: clinical magnitude-based inference, odds ratio magnitude-based inference, and non-clinical or mechanistic magnitude-based inference. A critique by Welch and Knight is that it is not clear which method should be used. When is something clinical and when is it really non-clinical? The choice can influence your conclusions. The suggestion by Hopkins here is as follows. If you decide to use the effect of your study as the basis of an intervention in the hope of improving anyone's health, wealth, or performance, then it's clinical. So even a simple comparison of males and females would be clinical if you decided based on the intervention findings that participants with low testosterone are much nicer people, so you will give men testosterone blockers to make the world a nicer place. So if it is an intervention, clinical magnitude-based inference is usually the most appropriate choice. Nevertheless, there is no hard decision rule for using clinical and non-clinical magnitude-based inference, and it remains therefore a bit subjective and a limitation of the method. Another major point of critique is related to the error rates in magnitude-based inference, which refers to the number of incorrect inferences made. Welch and Knight argued that magnitude-based inference had high type 1 error rates, false positives where you conclude the effect is substantial while it is actually trivial. Magnitude-based inference reacted that Welch and Knight used incorrect definitions of the errors and therefore incorrectly found high error rates. I will explain this issue with an example. We assume the true effect of an intervention is trivial in the population, as indicated by the purple confidence interval in the image here, the upper one. Welch and Knight proposed that a type 1 error in magnitude-based inference is committed when a true trivial effect could be possibly trivial and possibly substantial, as shown by the second confidence interval. In other words, the chance of trivial and beneficial are both larger than 25%. It makes sense to me to say that this is an error because you could incorrectly conclude that the effect is beneficial while it is actually trivial. In response, magnitude-based inference states that only when the confidence interval does not include trivial effects, as shown here, and therefore a trivial effect is very unlikely trivial, a type 1 error is incurred. This definition of a type 1 error also makes sense to me because only in this case you are quite certain that the effect is beneficial while it is actually trivial. I think both of them have a point here. I agree that it could be an error when the effect is actually trivial, but when the chance of benefit is quite high, as in the second interval. But on the other hand, in the case of the second interval, when it could still be trivial, so I can also understand the argument from magnitude-based inference that in this case there will be no real error. Using simulation, Hopkins and Bannerham showed that using their definition of errors, the inferential error rates for magnitude-based inference are sometimes lower and otherwise acceptable. They also showed that lower publication bias and better publishable outcomes with magnitude-based inference. But there is more critique related to the error rates. In a recent paper, Sarnani further criticized error rates and the definition of the error rates in magnitude-based inference. I will explain her critique using the same example. Again, we have a true trivial effect as shown by the first confidence interval, here, the purple one, and the second confidence interval shows the finding of our study. The conclusions based on magnitude-based inference would be possibly beneficial, as the probability of beneficial is 65%. However, it could also be trivial, as the probability for trivial is 33%, and it is therefore not very unlikely trivial, which would have represented an error according to magnitude-based inference. However, Sarnani criticizes this definition of an error, as most of the time you will in this case incorrectly conclude that it is possibly beneficial. In other words, if you conclude that an effect is, for example, likely positive when it is trivial, you are mostly wrong. And if you conclude that an effect is unlikely positive when it is trivial, you are mostly right. Sarnani therefore proposed that the degrees of error should be used based on the probabilities to calculate the error rates for magnitude-based inference. To understand this a bit better, I have provided here the qualitative statements used in clinical magnitude-based inference. For example, when the probability is between 25 and 75%, you would say it is possibly beneficial, as I also explained in the first video. Sarnani used the probabilities and qualitative statement to get the degrees of error. We use the same example again when there is a true trivial effect as shown by the purple confidence interval. If you then would find something like in the second confidence interval, with magnitude-based inference, you would say it's unlikely beneficial, as the probability of benefit shown on the right of the figure is within the range reported by magnitude-based inference for unlikely. Sarnani then used the mid-range of this probability as the chance of an error, so that would be 15%. In the third confidence interval, According to magnitude-based inference, you would use the qualitative statements of likely beneficial, as it is 76%, which is here the range of likely, and this would therefore be a probability of 85% for a type 1 error according to Sinani, which is the mid-range of likely. Using these degrees of probability, Sinani showed that magnitude-based inference has peaks of false positives, so type 1 errors, when the true effect is trivial in the beneficial direction, so it would be this area. So from effect size from 0 to 0.199999. And this peak of false positives using the error definitions by Sinani is shown in the figures here. For example, the left figure above shows the percentage of false positives for true trivial effect for null hypothesis significance testing in blue and non-clinical magnitude-based inference in green. The type 1 error rate is constant at 5% for null hypothesis testing, while for non-clinical magnitude-based inference, it depends on the sample size investigated. For example, at a sample size of 30 per group, the type 1 error rate, so the false positives, is around 30%, which is a lot higher compared to traditional hypothesis testing. And based on these high type 1 errors and the other high errors, Sinani also proposed that magnitude-based inference should not be used. However, as I also discussed 2 slides ago, Hopkins and Badaram do not agree with the definition of the errors by Sinani, therefore do not consider magnitude-based inference to have high error rates. For example, let's again assume we have a true trivial effect. According to a magnitude-based inference, the second confidence interval would be a false positive here because it is very unlikely trivial. However, the third confidence interval would be no error, as it is not very unlikely trivial. However, according to Sinani, this would be a type 1 error because you are more wrong than right. In response to the critique by Sinani, Hopkins and Badaram argued that by analogy with null hypothesis testing, there is nothing illogical or suspicious in declaring no type 1 error in magnitude-based inference in the third confidence interval when the true effect is trivial, and the probability for a trivial true magnitude is between 5 and 25%, so unlikely. They argue that the fifth non-significant confidence interval here should also be considered as an error in null hypothesis testing. Further, in magnitude-based inference, an unclear effect, so when the confidence interval overlaps all areas, is never considered to be an error as the inference is unclear. In other words, you don't make any inference from such an interval, so you can't make any error. However, also here Sinani disagrees and argues that when the true effect is, for example, beneficial, as shown by the second purple confidence interval, also a finding like this would represent a type 2 error, a false negative, as you incorrectly do not conclude that the effect is beneficial. Again, I see something in both arguments here. A second point of critique is related to the definition of the confidence interval. As we discussed in the previous video, in magnitude-based inference, the definition of the confidence interval is as follows. It represents the likely range of the population value of the statistic. For example, if the mean difference between groups is 10 kilo, as shown in the figure on the right, with 95% confidence intervals from 6 to 14 kilo, the true difference is likely somewhere between 6 and 14 kilo. However, the critique is that a confidence interval cannot be interpreted in this way using frequentist statistical inference methods, as we discussed previously. In this case, a probabilistic statement about the likely population values of the parameter is not allowed. So you can't say that the population value is likely between 6 and 14 kilo, as in the example above. If you construct 100 95% confidence intervals, then about 95 of these intervals will contain the population value. Typically, we only calculate a single confidence interval and not 100. This therefore gives us no way of knowing whether a single confidence interval happens to be one of the lucky intervals which contain the population value or whether it doesn't. It either does or doesn't, but we just don't know. In order to make statements about the probability of the population values, you would need to use Bayesian methods using credibility intervals. However, magnitude-based inference agrees and justifies their definition of the confidence interval by claiming to use Bayesian inferences. I will explain in a minute what Bayesian inferences are for those of you who are not familiar with this. The same critique is related to the probability statements in magnitude-based inference about the probability that the effect is harmful, trivial, or beneficial. Only Bayesian inferences allow such statements. Magnitude-based inference again justified this by claiming to use Bayesian inferences. We have been discussing Bayesian inferences a bit in the last few slides, so in order to understand the arguments about this, we have to understand what Bayesian statistics are, at least a bit. In short, you specify a prior belief about something which you quantify in a prior distribution. This reflects the uncertainty about the parameter before the experiment. Then you collect data. The posterior distribution is then calculated based on a likelihood distribution, which is based on the data and the prior distribution. This posterior distribution can be used to make probability statements about parameters, like the population value is likely within 5 to 10 kilo. Let's explain this a bit more using an example. Clinicians use a Bayesian approach informally when they try to diagnose a patient's problem. They have a belief about possible causes of the problem, and they probe for symptoms, test for signs of possible diseases, and order blood tests or scans or whatever to get the data that will make them their belief in one cause much greater than other possible causes. In this example, there is a patient that comes to the doctor with pain in the back of his leg. Based on his prior experience, the doctor thinks that it could be a sciatic nerve entrapment, which reflects therefore his prior belief. But he is not completely sure, as it could also be a hamstring injury or another muscle, injury of another muscle, such as adductor magnus. Therefore, he does a clinical examination and orders an MRI scan. Based on the results of the clinical examination and the MRI scan, shown here, he updates his posterior belief and comes to the conclusion that it is a hamstring injury and likely not a nerve entrapment. So, a prior belief, his sciatic nerve entrapment, is combined with data from the clinical examination and MRI scan to form a posterior belief, which is, well, it's likely a hamstring injury in this case. Now let's see a hypothetical example for a research study. Suppose you're interested in the effect of a certain supplement or training method on performance. You study this problem by conducting a randomized controlled trial on a sample of a population. Based on the results, you calculate the confidence limits. If you're a frequentist, you publish the confidence limits. But if you're Bayesian, you also factor in your prior belief about the effectiveness of the supplement or training, and you publish credibility limits, representing your posterior updated belief. For example, you might have believed that the supplement or training method had either little effect, and you were uncertain about this. In this case, you assume the effect could be anything with almost equal probability. The distribution in this case is represented in the left figure, the prior distribution. So you're not really sure what it could be. It could be almost anything, but you're probably sure it's around the effects around here. I don't want to quantify numbers for now to make it easy. Or you might have believed that there was a large, let's for example say a 5% enhancement effect, and you were really sure about this. So you gave this effect a small confidence limits, which is represented in the right image, shown here. Also, again, the prior distribution. Say it's around 5%, and you're really sure it's close to 5%. Could be a little bit more, a little bit less, but not too much difference. You then did the study and found a positive effect of, let's say, 10% with confidence intervals from 6 to 14%. If you combine these limits with your prior belief, you end up with a posterior belief, which in the right image is almost completely the same as the prior belief. You can see here, posterior belief, the blue line, is almost entirely the same as the prior belief. But in the left image, there is quite a difference between your prior belief and the posterior distribution. So your choice of a prior distribution affects your conclusions because we found the same results, which is represented here by the likelihood function. When the prior is a weak belief, as in the left image, the posterior is very similar to the likelihood. That is, the posterior belief is almost entirely dictated by the data. However, when we have a strong prior belief, our beliefs are not much altered by the data if the data have large confidence intervals to a small sample size. This has advantages and disadvantages. For example, if multiple previous studies show that a training intervention will improve performance, but your study finds it doesn't, by taking into consideration the finding of previous studies in your prior distribution, Your conclusion about the intervention is that it probably still works, and you don't conclude only based on one study that it doesn't work. There are also some disadvantages. For example, Hopkins and Bederam argue that the choice of the prior is subjective and that you can therefore essentially manipulate the data in a way to find the conclusions you want. If you want to show your supplement has a beneficial effect, you could, for example, quantify a prior distribution that shows a large effect with great certainty. Even if the actual data show no effect, the supplement will therefore have some effect if your sample size was not really large. Barker and Schofield suggested that multiple priors could simply be used to investigate the effects of the prior choice in analysis. On the right, you have a tweet by Alan Batteram commenting on this issue that you could indeed use multiple priors, but you then could still opt to use the one that gives you the results you like, again introducing potential bias in the conclusions of research. Another issue is how to quantify a prior distribution. Should you do this based on only the findings of a meta-analysis, based on the findings of a single other study that is approximately similar to yours, based on an expert opinion? Of course, the expert opinion is subjective and difficult to quantify. And if you use the findings of a meta-analysis or previous study, these studies have likely investigated something slightly different, and perhaps you expect the effect in your study to be different due to a different sample. For example, the previous studies used young football players and you will use old sedentary individuals, or they use males and you females. Therefore, the effect may actually be different, and in this case, you perhaps shouldn't use the findings from the previous study as a prior distribution. Due to these issues, Magnitude-Based Inference claims to use a flat prior, which assumes no prior distribution. With a flat prior, as shown in the image on the right, the plot reflects total uncertainty and a prior belief. All parameter values have the same probability of occurring. Therefore, the posterior probability will have the same shape as the likelihood curve based on the data if several other assumptions are met. Therefore, in Magnitude-Based Inference, the Magnitude-Based Inference confidence is equivalent to a Bayesian credible interval that has a specified probability of containing the true parameter value. And therefore, Magnitude-Based Inference also justifies the use of the Bayesian conclusions from the confidence interval. Barker and Schofield, however, argued that Magnitude-Based Inference doesn't use a flat prior, but a very specific prior distribution. Batson further argued that a flat prior distribution does not integrate to 1 and is inappropriate with small sample sizes generally used in Magnitude-Based Inference. Here the critique is that Magnitude-Based Inference is therefore simply a fundamentally incorrect approach. Magnitude-Based Inference is officially not doing Bayesian analysis by using informative prior distributions, but they interpret the confidence interval in the Bayesian way, which is not allowed without using the Bayesian methods. Therefore, some people have suggested that this is enough reason to stop using Magnitude-Based Inference in addition to the high error rates. And I can agree that this is problematic, but I would also like to add that I don't think that null hypothesis significance testing offers a solution to this problem. For example, Hoekstra and colleagues, which you may remember from the confidence interval experiment in the previous video, have shown that students, but also some researchers, and perhaps even you, incorrectly interpret the frequentist confidence interval in a Bayesian way, showing that null hypothesis testing actually has the same problem, although they officially not assign probability statements as in Magnitude-Based Inference. So, what should you do as a researcher, coach, or sports scientist? Opponents of Magnitude-Based Inference state that confidence intervals or a full Bayesian analysis should be used rather than Magnitude-Based Inference. Magnitude-Based Inference argues that there is currently no solution on how to make inferences with confidence intervals, and Bayesian analyses are not about to become universally adopted. So in other words, you can't use p-values or confidence intervals to make the inferences you would like to make, so you would need to do a full Bayesian analysis. In this regard, Mangerson and colleagues recently did a full Bayesian analysis with a flat prior and compared this to the results of Magnitude-Based Inference. They found small differences, on one hand suggesting that Magnitude-Based Inference is approximately equivalent to the full Bayesian analysis, but of course much easier to perform. On the other hand, they also suggest that Magnitude-Based Inference conclusions are not always correct. Perhaps you're thinking, well, why not? I'm not convinced by the critique on Magnitude-Based Inference and I still want to use it. And why don't I just take the best of each method and I do all of them? For example, let's say you would report both Magnitude-Based Inference and null hypothesis testing and let the reader decide on which method he would like to use to make inferences. Also here you have some problems, as based on the same data, the researcher favoring null hypothesis testing could conclude the intervention is ineffective in the first two findings, here, It's not significant, so the researcher could conclude, well, it's not effective, while a second researcher favoring magnitude-based inference concludes that the intervention is possibly beneficial in both cases. In the latter interval, we have a similar problem. One researcher favoring magnitude-based inference concludes that the intervention is ineffective, while the other one favoring null hypothesis testing could conclude that there is a significant improvement if he doesn't or she doesn't consider the effect size. So, what should you do? Back to null hypothesis testing, magnitude-based inference, Bayesian statistics, such as Bayesian magnitude-based inference, rope approach, likelihood ratios. Well, as I mentioned at the start of video 1, I'm no statistician and unfortunately I will therefore not be able to solve the problem of making inferences from data that has been around for decades already. I just hope I have provided some more insight into magnitude-based inference and the critique on magnitude-based inference, so you can make a decision for yourself if you prefer null hypothesis testing, magnitude-based inference, full Bayesian analysis, or perhaps even other approaches I mentioned. Personally, I do think full Bayesian analysis of magnitude-based inference and equivalence testing, for example, rope, are very interesting methods worth looking into. Equivalence testing is more comparable to null hypothesis testing, although the required sample sizes are also slightly larger than in traditional null hypothesis testing. Hopkins and Belleram also suggest that a second-generation p-value can be used in addition to magnitude-based inference to minimize type 1 errors. Yep. So here's a short list of some of the referred papers for further reading. Give the papers by Mangerson and Lakens a read if you're interested in a full Bayesian analysis of magnitude-based inference and equivalence testing. And of course, if you're interested in more details about magnitude-based inference or the criticism of magnitude-based inference, read the papers listed under each header. Thanks for listening, and of course feel free to point out any errors, to suggest improvements, or share the video if it has helped you to better understand magnitude-based inference and the critique on magnitude-based inference.